I'm a postdoc downstairs at JTCRI, and I got a PhD in public policy from the University of Maryland, School of Public Policy, and I will be talking about issues in international climate policy. Okay, so the agenda for today's lecture will be as follows. So I'll be giving you a brief overview of international climate policy. We'll cover topics from how international climate policy has moved from the Kyoto Protocol and how negotiations have moved towards the upcoming Paris Conference of Parties. And then we'll be covering some general overview of emissions reductions and technology transitions that are required to achieve some long-term climate goals. This is something that probably Leon has covered in some detail, but we'll be going over that again, just to brush up some concepts. And then I'll be talking about the impacts of near-term mitigation policy and the implications for the long term. And then we'll cover technology and climate policy, and finally a very brief overview of JTCRI's leadership in the road to Paris, negotiations. Okay, so let's begin with an overview of international climate policy. The global or the international body entity that governs international climate policy negotiations is the UN Framework Convention for Climate Change, otherwise known as UNFCCC, which was adopted in 1992, and currently there are 196 parties that have ratified this convention, including the United States. The main objective of the UNFCCC is to prevent dangerous anthropogenic interference to climate change. And among the most important international goals that the UNFCCC has adopted was in 2010, when they adopted the goal to limit global warming to 2 degrees C. The UNFCCC works on the principles of equity and something that's called common but differentiated responsibility, whereby the UNFCCC understands that to undertake action against climate change, everyone has different capabilities and different capacities, and not everyone can undertake action uniformly. The major activities that UNFCCC undertakes include emissions reporting, so this monitoring, verification, and reporting of emissions activities that are reported finally to the UNFCCC website by the different parties. And the other important activity of the UNFCCC is to undertake climate change negotiations. Okay, again, these are actually factual details that I want to cover just in a very briefly, just to give you an overview of how things have evolved over time. The Kyoto Protocol, which probably some of you have already heard earlier, was adopted in 1997 and entered into force in 2005. So this is one of the most instrumental protocols or agreements, international agreements, that went into force and recognized the severity of climate change and the need for action against climate change. The Kyoto Protocol places a heavier burden on developed nations, understanding that developed nations are largely responsible for the bulk of emissions that are in place in the atmosphere as of today, and it places very minimal efforts or minimal burden on the developing countries. The Kyoto Protocol essentially imposed some national caps on the GHG emissions of developed countries that have ratified the protocol, and at that time the US hadn't even ratified the protocol. And each participating country was assigned like an emissions cap. Okay, so each country was told how much emissions you have to reduce. And they established some different mechanisms, essentially to mimic a cap and trade mechanism, where you have a cap, and countries can just trade their emissions reductions with each other depending on their individual abilities. It was kind of, it was not exactly a cap and trade, but they tried to mimic the cap and trade mechanism. And we'll talk about the cap and trade.
Can you expand more on like the bank part though?
So they had some flexible mechanisms like joint implementation and a clean development mechanism where basically the developed countries could invest in technologies and emissions reductions in developing countries and then get credit for that.
Okay.
So although that's now past, and that's like the next slide basically covers it all. No one likes to be told that you have to be you know what to do, and that was an important failure of Kyoto Protocol, that it was top bottom. So each country was assigned emissions reductions caps, and just no policymaker likes that. So international climate policy is now moving towards a bottom-up approach, where countries come up with what they can do. They offer on their plate what they can do, and for example, in Copenhagen in 2009, countries pledged near-term emissions mitigation through 2020, and in the ongoing negotiations on the road to the Paris negotiations in December, that's like less than a month from now, countries are submitting what are known as their intended nationally determined contributions, or INDCs. Again, these INDCs outline emissions reductions commitments through 2030. Okay, so with that background on international climate policy, let's move on to what role do IAMs play in climate policy and climate policy analysis. So one of the key questions that IAM researchers have looked at is to analyze what it takes to achieve long-term climate goals. So we just covered in a couple of slides earlier that the UNFCCC has adopted a long-term international climate goal of limiting global warming by 2100 to 2 degrees C. Right. So now what does it take to achieve that? Okay. Now this is something that probably you've seen earlier. Again, we have to remember that global emissions have continued to rise over time, and the bulk of the emissions come from the carbon dioxide, CO2 emissions in fossil fuel and industrial processes, with other sectors contributing some percentage, including land use change, methane and nitrous oxide and F-gases. With these increasing global GHG emissions, the global concentrations of these emissions has also tended to increase over time, and the overall forcing, the radiative forcing on the atmosphere, tends to follow these different pathways. So this is the uncertainty bound that I picked up from the recent IPCC AR5, the fifth assessment report. So these scenarios that are out there in the literature suggest that without any additional mitigation action, global mean surface temperature is likely to increase in the range of like 3.7 to 4.8 degrees Celsius. And remember that the international goal is to actually limit global warming to 2 degrees C. So that implies that undertaking or achieving those goals are going to imply or are going to require drastic emissions mitigation going forward. Okay, but translating emissions or emissions or concentrations to temperature outcomes is not that straightforward. There are a range of uncertainties. I'm sure Corinne must have covered some of them. There are a range of uncertainties related to climate feedbacks, the global carbon cycle, and so on. And so it's not clear, or it's very ambiguous how to say or how to translate a given long-term climate goal to emissions or vice versa. And so there are two ways in which temperature goals can be expressed. So they can be expressed in terms of like medium or median long-term equilibrium temperatures. Like just say that this particular emissions level would lead to a median temperature outcome of X degrees Celsius. Or the more sophisticated way of expressing emissions, the relationship between emissions and temperature would be to express them in the form of likelihood of remaining below a particular level. And which is what the IPCC table kind of summarizes here. So for example, if we were to look at what should be the concentration levels, or what should be the emissions levels that would be required to achieve a 2 degrees C goal, you would see here that it has to be that the concentration, the GHG concentrations need to be roughly 450 parts per million, and the corresponding radiative forcing would be like 2.6, and that the RCP corresponds to the representative concentration pathways, which is, again, I don't want to give you much more detail on that. We can talk about it later if we want to. And the likely language that the IPCC uses is basically a way to make it available or make it more accessible to laymen who can't understand probabilities. So this is so likely represents greater than 66% chance. So the IPCC scenarios, they span a wide range of scenarios. There are a large number of scenarios, and the scenarios are grouped together on the basis of what is the likely, or how many scenarios achieve those particular targets with greater than 66% chance. Okay, so the bottom line is very clear from the previous discussion. So if you have to achieve, the world has to achieve some temperature outcomes by the end of the century, that is going to require deep emissions reductions going into the future. But the question that comes up right now is, what kind of technology transitions are required to meet those targets? Again, the IPCC is very useful in that respect. So we can see here that as the stringency of the mitigation policy, or the long-term climate target increases, you will see that the share of low carbon energy that is required in all these model projections tends to increase, right? So that's a key insight, that going forward, if you are going to implement stringent mitigation policies to achieve long-term climate goals, that is going to entail a dramatic scale-up of low and zero carbon energy. So here we just ran some technology and climate policy scenarios using GCAM, just to see the nature of transitions, just to get a broad sense for the character of transitions that would be required to achieve those emissions pathways. So we just ran 3 scenarios, technology scenarios, one with a full technology portfolio, one with no bio-CCS. Bio-CCS is basically biomass in conjunction with CCS, which is a very attractive option in many, not attractive, cost-effective option in many mitigation scenarios, because that tends to give for negative emissions on the whole. And then the third technology scenario, where we limited the deployment of CCS and nuclear. And then we explored a range of emissions pathways, where slightly declining from 2020 to 2010 levels. By 2050, I'll just show you the emissions pathways that we explored, and then declined to 25% and 50% below 2010 levels. So these emissions targets, the 0%, 25%, and 50%, they were identified in previous assessment reports as kind of consistent with some long-term climate targets. So these are the emissions pathways that we imposed, global emissions pathways that we imposed on the GCAM model. And again, something that you've seen before. So under the reference scenario, that is without any climate policy, you'll find that fossil fuels dominate the mix. So these bars here represent coal. This is gas, and that's oil. So you can see that the bulk of the energy consumption comes from fossil fuels. The no bio-CCS and no nuclear and CCS would be identical to these, because probably, as you know, in GCAM, the reference case, CCS doesn't come in. So maybe the no nuclear would be a little different. Okay, so as we increase the stringency of the emissions mitigation policy, what we see is that the general character of mitigation takes two forms. One is to switch fuel to low carbon sources. So you can see a switching happening to bioenergy, nuclear, and of course in the primary energy mix we can't see CCS here, but that's one of the key insights, that when you implement mitigation policies, there is a switch to low carbon energy, and there's also a reduction in overall energy. So I'm just going to run over that again. So you can see an overall reduction in the energy consumption. So that's the bar for energy reduction. So as you increase the stringency, there's more energy reduction and there's more fuel switching happening towards low carbon energy sources. And likewise in the electricity generation, right? So this is a reference case, and then as you increase the stringency, you would see more and more CCS coming in, IOCCS, which is the green shaded bars, and these become even more important in. This is the node. Okay, so these are important in the full technology portfolio scenario, whereas in the nuclear and CCS, you can see a rapid expansion of non-biomass renewables. Basically, those are solar and right.
Can you go back to the figures? Maybe just like run through these. Yeah, I was just looking at the full technology portfolio. It seems like when you increase your emission reduction, is that electricity generation? Okay, it seems that
It's increasing.
It's increasing. Yeah.
Yeah. So this is something I will be covering in a few slides, but you raised a very good question. The way these emissions mitigation scenarios were implemented were by assuming a uniform carbon price across the board. So basically, you set the emissions cap, right, according to the emissions pathways that I showed earlier, and then the model solves for those caps by applying a uniform carbon price across the board. So all sectors see the same carbon price, and it's and by virtue of that, it's most cost effective for the model to increase electricity production. So do some fuel switching, do some changes in the electricity generation, and then increase electricity generation use in the end use sectors, rather than switch fuel in the end use sectors. Does that make sense? It's just a cost effective solution.
Okay.
It's a cost effective solution. Like, it's just a market dynamic.
Okay.
Right? We'll go over that in a little more detail
Okay.
in a couple of slides. Yeah. So looks like Nazar's wife is. Okay, so the two key bottom lines from IM studies that I've covered so far is that more stringent long-term outcomes will require steeper emissions reductions, and the second is that steeper emissions reductions will entail more dramatic technology transitions, and that will entail more investment and also retirement of emitting sources, like we just saw in the slides earlier. It's not only a switch to low carbon fuel, but as you can see, let's just look at this bar, which is the purple or violet bar. So as you increase the stringency, you see that a decrease in coal-fired generation and even other emitting sources. So that's a generic insight that most of the IM studies have consistently given over time. Okay. Now the question that comes up here is, okay, we know that long-term temperature outcomes will require stringent reductions. We know that it's going to entail some dramatic technology transformations. But what kind of real-world policies can you actually implement to get those reductions? So policymakers have a number of instruments at their disposal. One is, which is one of the common techniques is, just to give a regulated emissions control, which is basically a command and control. It's like a decree, it's like a law, that all parties within an entity are, they're not allowed to use technology that emits more than X gigatons or something like that, or something like a rate-based constraint. Like coal-fired power utilities are not allowed to use technology that would lead to that would emit emissions of say X tons of carbon dioxide per unit of megawatt hour or something like that, right? So that's a command and control approach. But the more popularly economists tend to like this approach, which is a market-based approach, wherein you price emissions. So every unit of emissions would be taxed, right? So you impose a price on that. And the other thing, the other method is to do emissions trading, which is what I was talking about earlier, like a cap and trade. So you impose a cap, and then allow the parties to trade the emissions reductions between or among themselves, depending on their own cost distribution. Like for example, one coal-fired power plant utility might have some difficulty in switching to a low emitting technology. In which case, that power plant can just buy emissions reductions from another plant, which can actually switch to a better fuel, right? And then there are technology-focused policies that you can give subsidies to conduct R&D, like the US does. There are subsidies to invest or to do research in nuclear and improve nuclear technologies. And then there are technology deployment policies where you can give subsidies to actually adopt technologies. For example, in China, there are these development banks which essentially give 0% interest rate for adopting technologies such as solar. So if you want to apply for a loan, if a utility just wants to apply for a loan, they're willing to give you a 0% interest rate to encourage the deployment of solar. And among these options, the most cost-effective, meaning the least cost option is to go for a market-based policy instrument. So either emissions tax or emissions trading. I mean, this is something that has been well established in the environmental economics literature. So now the follow-up question is, how do models represent mitigation? Like, how do we do mitigation? We say, okay, you need to achieve these long-term climate goals, you need to have these emissions pathways and so on. But how do we actually achieve those mitigation pathways? Any guesses? You all know you've done some experiments using GCAM.
You model them.
Sorry?
You model them.
Yeah.
We model
Oh,
them.
how do you model
How do we model them?
We use Pathfinder to limit the emission target.
Okay, the hint is that the answer is here. Are we using a command and control? Are we saying that all the utilities have to have some kind of emissions per unit megawatt or something like that?
The models just put a cap or a tax on it. That's all.
Exactly.
And you
So
price
we
it.
tax emissions to achieve a given emissions constraint, right? So when you run the 450 cap, right? That's the thing you did. So excuse me, did anyone ask you to pull out the carbon price trajectories for that? No. Okay, the next time you can do that, and I think I'll be asking you to do that on my side. So you can just pull out the carbon price trajectory. So basically what you do is you specify a target, and the target is achieved by imposing a tax on emissions. Okay. Now there are two ways of looking at that problem. So one is that you're taxing emissions. The other way of looking at that problem is that it's just a emissions trading mechanism with a price on carbon. The two are different. Okay?
But
Do you understand?
But both apply a price.
Sorry?
But both apply a price to carbon, just in different ways.
Yeah. But the perspective is different. When you say carbon price,
Yeah.
the implicit assumption is that there is a market for carbon,
Yeah.
and that parties are trading amongst themselves.
Yeah.
But a tax is like a government thing. It's like
Yeah.
someone is imposing a tax. Okay, so someone is actually like paying for that. So there's a difference between a tax and a price. Both the perspectives are valid. You can assume that both are happening. The common way, or the more defendable way that most researchers tend to approach the issue is to say that this is an emissions trading. You're just assuming that it's a cap and trade. So there is an overall global cap of whatever million tons of carbon dioxide that you specify in your input file, and that is being achieved by the parties by just trading emissions reductions across the board. So there is a price on carbon. Okay. Okay. Yeah.
So the FFICT and the UCT GCAM files we've used before, they're entirely market.
It's different.
Or is that
those are like
different?
Yeah, it's like
They're different.
Okay.
So the FFICT is just assuming that that carbon dioxide emissions coming from only the energy sector can be traded or can be taxed, whatever way you look at it, right? Whereas the UCT assumes that it's just the price can be applied on all sources of carbon dioxide, including land use change emissions. Does that answer your question?
Yes, yeah. So,
Great.
so it's
Okay.
not like there's a technology policy in there.
There is no technology policy. We don't. So exactly. So we don't model technology policy as a default case. But if you wanted to go ahead and do that, that's totally fine. In fact, that's what I think I have here. Yeah, exactly. So I just have that as a second bullet point here. So let me just go over this slide first. So as I explained to you, most models represent mitigation action by imposing a tax on emissions, which can also be seen as what is called a shadow price. Okay, which is basically you have a constraint, so what is a corresponding shadow price of that to achieve that constraint. Okay, the shadow price is the price of the implicit carbon market that I was talking about earlier. Right? You can also look at it as a carbon market for carbon that has some buyers and sellers, and they see a price. Right? So that's the shadow price. So other approaches can also be actually modeled explicitly. For example, in the US you have this Clean Power Plan, which has been put up recently. Then there are these CAFE standards and so on. Right? Those can actually be modeled in any model, any of these IMs, not only GCAM, although GCAM is the best. However, that tends to be a little more complicated for the kind of insights and recommendations that we are often looking for using IAMs. But if your particular problem warrants modeling of actual policies, you can actually go ahead and do that. There's no problem. But in most global studies of global level and economy-wide studies, people typically tend to assume a carbon price approach, right? Yeah, so it's a widely accepted and it's a very simple way of modeling long-term mitigation, and it's very useful to give generic policy insights. Okay. However, as I will be showing in a while, it is very important to understand the implications that the carbon price approach would have for the distribution of mitigation across regions and sectors. So when you're looking at global scale or economy-wide scale insights, it tends to be fine, I mean, reasonable. However, if you're going to look at something like sector-wide, or if you're going to say how much emissions reductions are happening because of this mitigation policy, how much of that is coming from electricity, how much of that is coming from industry and transport and so on, those insights need to be taken with a pinch of salt, because they don't actually mimic real-world policies, right? So, and that is something that I'll be showing you in a couple of slides from now. So, any questions so far? I think I've been speaking for quite a while. Okay, cool. That's great. Okay, so again, I'm just trying to raise questions as they come up here, right? I mean, now the immediate question is, okay, you say that models represent mitigation by means of carbon price or carbon tax. So how do you actually reconcile that with how people are actually undertaking policies, right? So as I just mentioned earlier, the US is going to reduce emissions in the electricity sector, but not by imposing a carbon price across the board, no, right? The cap and trade mechanism in US is probably never going to happen because, at least in the near term, the Senate recently just vetoed that and so on. So a carbon price across sectors is not going to happen in the US, okay? At least in the near term. The US envisions near-term policies to reduce emissions by means of sectoral approaches or sectoral regulatory approaches, right? So they have the Clean Power Plan in place, not in place. It's going to come in force in a while, in sometime soon. And then CAFE standards are already in place, right? These are the fuel economy standards in transportation, and so on. So real world policies, in short, are often bottom up. They're never top down, right? It's not like one entity or one body is going to give you give an economy-wide cap, and all parties are just going to actively participate to achieve that. No, that seldom happens. That has seldom happened in the past also. So in that sense, the carbon price approach is just like a benchmark. So assume that you have a study where you're going to actually model the Clean Power Plan or the CAFE standards. So it's just customary. It's like traditional approach is to also run a case with the uniform carbon price across the board, and then use that case to compare against this. Because first and foremost, the carbon price approach is cost effective because it's a market solution, right? It doesn't require any. There are no. I don't want to bore you with a lot of economics jargon, but there are no transaction costs, limited transaction costs involved, and so on and so forth. And policymakers are often interested in such least cost solutions. Right. Okay, so just to give you a sense for how sectoral distributions can be vastly different compared to real world policies when you implement them in models. Here's is a case that we ran using GCAM again. So this is the US greenhouse gas emissions pathways. That's the reference case, and this is a mitigation pathway that is consistent with some of US's commitments in the near term. Okay, so the US has committed to reducing emissions by 17% relative to 2005 by 2020, and this was in Copenhagen. And the US's INDC, to refresh, INDC stands for Intended Nationally Determined Contributions. A very fancy name, simple, it's just emissions reductions, given in different forms. So the US's INDC commitment, or the commitment for the upcoming Paris negotiations, is that they would reduce their emissions, greenhouse gas emissions, by 26 to 28% by 2025. Okay, and in this particular run, we just assumed a 27% reduction by 2025 and a linear pathway going forward.
So does the projection start from 2010 or 2015 in this case?
The percentage,
open the door for
The
Tom.
projection, so the projection,
these should be from 2010.
okay. So I just wonder like why there's like going down.
Oh, why is it going down? I think for a couple of reasons. One is I think this particular scenario assumes no new coal coming in 2015. So for example, we just ran a case where we just assumed that there's no new investments in coal-fired plants coming in the electricity generation. That's not a default scenario. It's just a scenario that we had to run for a particular purpose. Okay, so as I mentioned earlier, the mitigation scenario, we just ran it by assuming a uniform carbon price throughout. So now let's see the impact of that on the sectoral emissions mitigation. So this is emissions mitigation. These are emissions by different sectors. So you can see buildings, transportation, industry, then you have electricity, and then a teeny tiny land use change. I think probably I deleted that. Maybe I deleted it. And then you have methane, and then nitrous oxide, F gases. F gases form a very small portion of the overall emissions. So in the mitigation scenario, which is basically achieving those emissions reductions by means of carbon price, what you can see is that, I should probably mention that earlier, but I'll talk about it later. The implication of a carbon price approach is that the dirtiest sectors are the worst hit. So in the baseline case, that is in the no policy case, you can see a large portion of the emissions coming from electricity. And so that is going to be the sector that is going to be worst hit in a carbon price approach. Okay? And you can see that it's talking about like 70% reductions from 2005 by 2030. Right?
What's the other big one? Is that buildings?
Sorry?
What's the other big one? Is that buildings?
Oh no, the other big one is industry. This is industry.
The one below that.
The one below that should be transportation. But I'm going to talk about that just a little bit. So there are two things here, okay? So in a uniform carbon price approach, dirtiest sectors are worsted. Also, the carbon price approach favors more supply side transformation rather than demand side transformation. That brings us back to Lou's question. So the uniform carbon price is basically saying, equal marginal costs of abatement across sectors. And by equal marginal abatement costs, what I mean is that every ton of carbon that you abate, okay, the price for that or the cost for that is just equal across the board. And as a result of that, dirtiest sectors are hit more. It's just cost effective, right? It's just most cost effective to attack the sectors that are emitting much more than the ones that are not. And it makes more sense to actually do all the transformation on the supply side rather than on the demand side, right? That's probably something as an example exercise. I should have probably included that slide, but so you can just assume equal marginal abatement costs, and you can try to run your own. Maybe in our TA session next week, I may try to give them a little more background for those who don't appreciate that much. So any questions here? This probably gets to your question, right? So when you apply a carbon price, you just prefer a lot of transformation happening on the electricity or any other transformation cycle. In this case, it's mostly it's electricity, because electricity is extensively used in the end use sectors. So you put it's most cost effective to do all the fuel switching and do all the transformation in electricity, and then feed the cleaner electricity to the end use sectors. Any questions there? So what I want you to note here is that this 70% reduction from 2005 in the electricity generation sector, assuming a uniform carbon price across the board, is so vastly different from what the clean power plan is envisioning. Does anyone have, except for Lou, does anyone have a sense for what the clean power plan is envisioning? So they are envisioning a 30% reduction, okay, 32% reduction by 2030 from electricity. So as you can see, the value of the carbon price-based approach is just to compare against actual real-world policies. Real-world policies might not be implemented in tandem or just according to what the equal marginal abatement cost or the uniform carbon price approach suggests. Okay, so again, I just wanted to reinforce this point, because it's very important that you interpret the results that you get from IAMs correctly, especially for policy making. Okay, so that was about kind of a static policy model. You have a mitigation cap at a given point in time. How would you model that in GCAP? The other question that most modelers are interested in looking is, how do you model policies over time? Right? Often, IAMs are used to produce some solutions for achieving some long-term climate goals, like 450 ppm CO2e, or limiting global warming to 2 degrees C, or so on and so forth. So how do you actually model those kinds of policy targets, long-term targets? So in one of the readings that I'd sent out, I'm not sure if you guys caught it. So this Peck and Van, they show that the cost-effective solution. Again, cost effectiveness is something that most economists are just obsessed with. We all, whatever. So the cost-effective method of achieving those long-term climate goals is to employ an exponentially rising carbon price, right? So if you run your 450 ppm cap, and if you look at the carbon price trajectories, they will be roughly exponential. Okay, that is by exponential I mean like a fixed percent increase per year, right? They may not be exact. The reason is, for different reasons, the policy file that is being given to you is not like it's not a target finder. So it's not like it's not like you have actually achieved the 450 ppm target, but it's just like an approximation. However, if you look at the carbon price trajectories, they should be roughly exponential over time. Okay. So now, what are the implications of this exponentially rising carbon price? To understand that, we can look at the scenarios that Leon and team ran for one of the not a model comparison, but one of the international climate policy related research. So they ran different suites of technology assumptions. Okay, so they have a reference scenario, which is the most pessimistic of the whole lot. So that assumes no CCS. That also assumes very pessimistic growth of bioenergy, and then reference cases basically just standard assumptions about hydrogen, end-use energy efficiency, renewables, and for nuclear power, it's very pessimistic. It says no new builds. Okay, so that's the reference scenario, and then there is this bioenergy CCS scenario, which is basically saying you can have advanced CCS, you can have advanced bio and hydrogen, but all the other technologies are just left in the reference case, like the standard assumptions, reference assumptions. And then there is this renewable nuclear and efficiency scenario, which just basically assumes cheaper nuclear and renewables going forward, okay, in the future. And the most, and the most optimistic scenario of the whole lot assumes advances in all technologies, right? So that's very optimistic, assuming that all low carbon technologies, low emitting technologies will be cheaper going forward. Yep.
Why do you bundle like that with the between reference and advanced, right? So why can't you have advanced, wind and CCS?
This is just a technology suite assumption that was made for this study. It just to, again, to give very generic insights, not to go into particular details. A more detailed version of this study was done for CCSP.
Okay.
Yeah, those reports. I think that report is available online. You can also look for more technologies. I mean, there are n number of possibilities here, right?
Yeah,
you can
I just
go step by
wondered if
step.
you knew why they bundled it like with those three.
Yeah. So some key technologies were bundled together.
Yeah.
Renewables and nuclear bundled together. CCS they make it separately, and they included bioenergy along with CCS because of the character of the combination.
Yeah.
Like that offers the negative emissions option. And you'll see the interesting feature of these different technology paths. Okay, so here are the carbon price trajectories. All these scenarios are assumed to achieve a 550 ppm concentration target by the end of the century, right? So in all of these technology scenarios, you can see that the carbon price is exponentially rising. So that is like an input condition that is set to the model. The exponentiality of the carbon price trajectory is something that is fed to the model, okay? And as I explained earlier, that is to meet the Pick-and-Van cost effectiveness criterion over time, right? The emissions pathways are vastly different. Now let's just deep dive into those emissions pathways a little bit. So a key virtue of this exponentially rising carbon price trajectory is that the social planner is like, some people in our office like to call the social planner the God. In a sense, that is what it is, right? I mean, it's like, sorry for those who are not religious, but it's in a sense, it's the decision maker in the model that can actually allocate emissions over time. So that social planner can make the social planner that can make policy level decisions, right? Because GChem doesn't have government. I'm avoiding the use of the word government. We don't model the government. So that social planner can actually allocate emissions over time, right? So now that social planner can see that in the bio-CCS scenario, there is availability of a negative emissions technology in the future, which means that the model can afford to emit more in the near term and then emit less going forward, right? So this allocation over time is a unique feature of the exponential increase of carbon price. So that it's just allocations of emissions over time, and that's an ability that the policy, it's an implicit ability. It's like the policymaker or the COD knows everything, and they just know what's going to, how technologies evolve in the future, and they can just make the decision to emit more today and emit less going forward, and still meet the same long-term climate goal, right? So the key insight over here in this exercise is that, technology assumptions, depending on the different levels of availability, the levels of advance of technology, would influence how much models or how much scenarios generated by models emit in the near term versus long term. That trade-off will depend on technology assumptions. Okay. Okay. That brings us to another interesting topic that has been explored in quite some depth in the IAM community. That is the near-term policy versus long-term outcomes. So how do near-term policy choices impact and influence the long-term climate outcomes? Okay, so back to some science. The recent IPCC report, that's the 5th assessment report, has shown that temperature change is almost linearly correlated to cumulative emissions, cumulative CO2 emissions across a century. So basically, if you are saying that the international community needs to achieve a long-term commitment of limiting temperature to 2 degrees C, you can almost translate that long-term outcome, temperature outcome, to an associated cumulative emissions target. So let's just look at that table. Let's just focus on this part here. So the 2 degrees C goal is an international community goal. It's something like that the UNFCCC has adopted. So that's of key interest. So if you want to achieve a 50% chance of limiting, if you want to limit long-term temperature change to 2 degrees C with a 50% chance, the cumulative emissions associated with those are 1,300. So this is something that the IPCC has found out by running a range of models and come up with this key insight here. So now that means that the near term and the long term are very closely coupled. Okay, so because climate forcing now is basically a cumulative emissions problem, right? Cumulative emissions meaning sum of emissions over time, right? So how much you do in the near term is going to impact how much you are going to end up doing in the long term to achieve the same goal. Simple, right? So the policy relevant question that comes here is, for all these different commitments that countries have been making in the recent past, do these align with the cost-effective trajectories to limit global warming to 2C? And the second question is that what are the implications for the long term? Because just as I explained right now, the forcing is like a cumulative emissions thing, right? So if you do less now, you have to do more later, right? So it's not as simple as that. It's just not. I mean, it sounds very simple. Yes, it is simple, but the doing more later is going to involve dramatic transformations and could also have implications for the feasibility of achieving economic feasibility of achieving those long-term targets, and that's the topic that I'll be discussing in the next few slides here. Okay, so the study of interest here for this particular topic is the Riai et al. Paper, which again I had circulated. So this logged into Copenhagen Pledges paper. So basically, this is a model intercomparison exercise which is called Ampere. Please don't ask. Oh, you have the expansion of it. It's a very complicated one. Assessment of climate change mitigation pathways and evaluation. Blah blah blah. So that's a very important exercise that was led by Europeans, and it fed into the IPCC's 5th assessment report. Okay, so basically in this exercise, they specified like low and high near-term targets, that is targets through 2030, and they imposed century-wide cumulative emissions targets, right? And then they also explored a range of technology sensitivity, like They assume like full portfolio of technologies available, no new nuclear, no CCS, limited biomass, and so on, and some more technology sensitivities. This is the overview of this study. Okay, the key finding of this model intercomparison exercise was that the near-term commitments do not align with cost-effective pathways. So these scenarios over here, they are the ones that show delayed action. Delayed action meaning mitigation action that is implied by commitments that different countries have made. Okay, so they just put those all together. Again, they modeled only the Copenhagen pledges, which were made in 2009, and not the recent INDC pledges, right? And then they just made some extrapolations through 2030, and then they found that these pathways just don't align with this green set of scenarios, which are the trajectories that lead to cumulative emissions budget with the cost effectiveness criterion implied on that, exponentially rising carbon price, equal carbon price across the board, and so on. So that implies that because these delayed action scenarios did not achieve emissions mitigation, as much emissions mitigation as the cost-effective scenarios, these scenarios imply much more drastic reductions going forward. Right? Now, to place those rapid decarbonizations in the future, this paper also compared historical distribution of decarbonization rates. Decarbonization meaning just emissions, change in emissions reductions. No, change in emissions, right? So emissions growth rate, right? They looked at the historical distribution, and so you can see that the historical distribution is kind of tilted towards emissions growth, right? So this signifies growth, and the negative axis actually signifies emissions reductions, right? So this distribution as a whole is skewed towards growth. So which is obvious, right? Which is very easy to understand, because countries have, many countries have undergone rapid economic changes and economic growth leading to increase in emissions rather than decreasing in the past. On the other hand, the immediate action scenarios that envision immediate and strict climate change mitigation policies starting 2015, right? Those scenarios imply decarbonization rates of roughly like 2 to 4%, and the delayed action scenarios imply even stringent decarbonization rates, right? So they're asking for much more than what has been observed in the past. Now, to place some of these numbers in context, the tail ends of this distribution were mainly achieved during very drastic economic situations or economic circumstances. For example, in Europe during the World War I and II, or during the collapse of the Soviet Union, and some decarbonization rates of like 2 to 3% have been achieved because of mitigation policies. Like for example, in France, the French decided to scale up nuclear. I think the period was probably 1980s to 2000 or something like that. And during that period, emissions from in the French economy went down. Okay, so such decarbonization rates have been observed in the national scale. But imagine achieving such dramatic decarbonization in the future at the global level. So you can just imagine how much effort that is going to take, right? So that is the whole point of this paper, that the commitments that have been made so far that are implied by these Copenhagen pledges, and like we found out in another paper that we are publishing in a few weeks from now, implied by the recent commitments by different countries for the Paris negotiations, right? They do not align with cost-effective pathways, and those will actually entail dramatic emissions reductions going forward, and the pace of emissions reductions that will be required is kind of scary for many people, because that is not being observed in the past. But that doesn't mean it's not achievable. No, it's just that we just have to that's the kind of insight that you get from IAMs, that it's going to take a lot of effort. Okay, yeah.
Can you comment on how these medium and delayed reduction rates would look past 2050? Maybe
I think
2050?
it's in the figure,
Okay.
in the original paper. I just pulled them out from here for the sake of the presentation. But 2050, post 2050
Yeah, I was
rates are
wondering
not.
if it go this way
Sorry.
or this way.
The post 2050 rates are actually not so important, as you can see from the emissions scenario. Much of this action is actually happening in the medium term, and then emissions rates actually slow down, right? But again, you just want to keep in mind that these emissions scenarios over here, they are dependent on a range of technology assumptions. So this covers the full range of technology sensitivities that I put here. In fact, there are 4 more bullet points that I will fit in here, right?
Just quick qualification. The question, if you delayed beyond 2030, I mean, it just becomes obviously more extreme if it was 2035.
If you delayed
Yeah,
beyond
if you
2030?
delay because of political, I mean, all those
Oh,
other
yeah,
things,
that's
then it
true.
gets just worse and worse.
Yeah, it gets much worse.
And possibly
sorry.
possibly not resolvable.
Actually, there are scenarios that are infeasible and that are not being showed in this figure here. That's a very good point. Thanks for raising that. So this emissions figure does not include those scenarios that did not solve. Okay, so there are many scenarios that really were not able to achieve the stringent cumulative emissions budget, given the technology constraints. There are technology constraints can happen because of a range of political reasons and so on and so forth. Like I'll be talking about in a bit, and countries may not be willing to commit to emissions reductions in the near term, and in those cases, some scenarios can be rendered infeasible. In fact, our team also contributed to one study for this paper, and that we had explored the case where you just don't undertake any mitigation until 2050, I think, and then the model just collapses. It's just not possible. You cannot do anything, even if you have the full suite of technologies, and if you increase your iterations, Okay, so a little bit more on the future challenges of delayed action. So, I told you upfront earlier a while ago that the scale up of low carbon energy is something that's very important in most mitigation scenarios. And the scale up of low carbon energy becomes even more important in the delayed scenario. So this is basically the optimal OPT scenario that you will be seeing in the main figure of the paper. LST, this stands for low short-term target, which is not as ambitious as which is a more ambitious short-term target compared to a high ST, which is a high short-term target, right? So in these delayed scenarios, you can see much more rapid scale-up of low carbon energy happening as compared to the optimal, which is the cost-effective scenarios.
I'm sorry, I'm having trouble understanding the y-axis. It's just the adoption.
It's just the share of low carbon energy
okay.
in the primary,
all right.
total primary.
All right.
Okay? Is that clear? I mean, this is just a very generic, simple insight. But we have to remember that it's not only the acceleration of low carbon transformation that is a challenge. What is also challenging under delayed mitigation action is dealing with the consequences of what's called a lock-in into fossil fuel sources of energy, right? And for example, if you did not have any mitigation policies in place in the near term, you are basically encouraging the energy system to evolve as it is right now. That is just dominate, to allow fossil fuel sources to dominate the future. And if that's going to happen, one fine day in 2030, people decide, some people in our office like to call that day the day of reckoning. So on that day, people decide that climate change mitigation is so important, right? What's going to happen? You're just going to retire all these investments, right? So it's just going to be, all those assets will become these stranded assets, right? So that is also a key concern with delayed mitigation action. Okay, to summarize, this is just for people who like to look look at things from an economics perspective. So this is just a global marginal abatement cost curve. So what this plots is a carbon price on the y-axis, and this plots abatement on the x-axis, right? So different levels of abatement will require different levels of carbon price. For simplicity, I've just made a linear curve. It may not be linear. It's just the requirement is that it's convex. It's mostly convex, and it's a convex function. The price is a convex function of abatement, and I just assume for simplicity here to be linear. Okay, so you have two marginal abatement cost curves here. So one is a one that represents delayed action, and the other one is a one that points to early action, right? So now let's first understand why we think the marginal abatement cost curve will be lower for early action compared to delay action, right? Okay, so first of all, the marginal abatement cost curve with earlier action will be lower because early action will avoid locking into fossil fuel technologies, right? I just explained to you that if you're going to dramatically reduce or retire a whole bunch of fossil fuel fired power plants, that's going to be more expensive compared to just doing a gradual retirement over time, right? So early action is going to save on that. And the second reason is that early mitigation action will also foster investments in low carbon sources of energy, right? So if the world as a whole decides that climate change mitigation is an important problem, let's start investing in technologies like nuclear, solar, CCS, and so on. You have made all this investment in the next few years, right? And those investments will pay off in the future. Those technology options will become cheaper going forward, and that will push the marginal abatement cost curves for earlier action further down, right? So the moving down of the MAC curves for early action happens because of these two reasons. Although I didn't pull those effects apart here. Now, early action would also require lesser mitigation going forward, right? So you do more now, you have to do less in the future. So future abatement is going to be lesser under the early action case, right? So on the whole, early action is going to be cheaper going forward, right? And in summary, most of these studies that I just showed you, like Ampere and even in the IPCC, they have found that early action is going to be cheaper overall compared to delayed action, although delayed action will be cheaper in the near term, right? So delayed action is going to be cheaper now, but that's going to be much more expensive going forward. Okay, so that's the key insight that a lot of these studies tend to provide us, and also one of the upcoming studies that we are publishing in the coming few weeks. Okay, so the next topic that I thought would be interesting to talk about is technology and how that interacts with international climate policy. Okay, so it's clear from all the discussions that we had so far that technology has an important value, right? So if you have advanced technology, if you have cheaper technologies going forward, that is going to reduce the burden of mitigation, right? As you can see here, and this is the Clark et al. Study. So again, the reference technology scenario represents pessimistic technology options, and the advanced technology scenario represents very optimistic assumptions about technological change, that is how technological improvements will occur over time, and how cheap the technologies will be in the future, and so on. So you can see here that there is value to advanced technology. So when you have cheaper technology options, you have the cost of achieving a given mitigation goal is going to be cheaper, right? So there is a global value in investing in technology and technological change, right? So this is something that we can appreciate, hopefully. But the question that comes up right now is, okay, technology has global benefits. How about domestic benefits? Because ultimately, there's no God, there's no. Sorry, I didn't mean
There's
that.
no GCAM God.
Yeah, there's no GCAM. I didn't mean that. So, there's no international entity that is actually going to invest in technology. The investments in technology are going to come from domestic decision makers, right? Domestic or regional decision makers, right? So for example, there's no global body that says, okay, let's start investing in CCs. It's like US decides, companies in US, multinational firms in different places, they decide, okay, let's start doing some research on these technologies, or let's start investing in those technologies, right? So how do you reconcile the global benefits of technology versus the domestic benefits of technology? So in order to explore that, Leon and team, they explored they did this very nice experiment. So in one scenario, they said, okay, only US can have advanced technology, right? No, rest of the world cannot have advanced technology. Only US is going to invest in technology, and they're the only ones that are going to have that advanced technology, right? And in the second scenario, the scenario is constructed such that the advanced technology is just available all over the place. Okay? So basically, they're saying the US is like being large-hearted. They're saying, okay, we are going to invest in technologies, and we'll just make it available to everybody. These are kind of unrealistic, but then very powerful. It's a very powerful experiment to understand some things that you're going to see here. Okay, so now let's look at the global mitigation cost. Okay, so this is just the total cost of achieving the climate policy. In this case, it was the 550 ppm scenario under the two scenarios. I know there are 4 scenarios, but let's just focus on the 2 that I have marked here. Okay, so this is the enemy scenario where the US is like, the advanced technology just belongs to me. And this is the French scenario where like US just shares their technology with the rest of the globe. So it's very obvious from here that benefits for the globe are greater if advanced technologies are available everywhere. It's very easy to appreciate that. You have cheaper technology options available for throughout the globe, so it's just going to be cheaper overall to achieve a given climate mitigation target. Right? That's very, very, very obvious. That's pretty clear. So before I show the next part of the slide, can you guess, or what is your intuition about the direction of the costs for the US? So would the costs for US be greater in this scenario or in the global advanced technology scenario?
Global advanced technology.
Less.
I need a reason.
You need a reasoning?
Yeah. I mean, okay, by virtue of the fact that I'm asking, it means that it's going to be what you said.
Well,
But standard intuition, but intuition would say that okay, the US has cheaper technology, so you have to meet a mitigation target. So the cost for US have to be lower, right? That's if you just close your eyes, that's what you expect. But like Cole rightly.
Not if we have to spend more dollars for other parts of the world than.
Sorry.
Not if we're paying for other parts of the world with our dollars.
Right. I mean that's like somewhat standard intuition that okay, US has cheaper technology, so they should probably have lower cost. But that's not what happens. The benefits for the US are also greater if advanced technology is available all across the board. So a French scenario is something that even the US will benefit from, right? Now let's look at why that is the case. So there are 2 effects in place here. So one is a direct effect of advanced technology. So having advanced technology is going to reduce domestic costs, right? That's the effect that we all think about, right? So US is having cheaper technology, and that means that to achieve a given emissions reductions target, it's going to be cheaper for the US. That makes perfect sense to everyone, right? However, there is also an indirect effect. Now, because the US has cheaper technologies, right, and because the emissions reductions that these advanced technologies are going to achieve is a public good, it's not applicable only to US, it's also going to apply to the globe as a whole, right? So because of that effect, the US is going to be induced to undertake more emissions reductions by pure market factors, because that's most cost effective. The US has cheaper technology, that the US do more, right? So so it's this effect that leads to higher costs for the US, even if US has the cheaper technology. Does that make sense? Think about it. I'll give you a minute to think about it. Yeah.
Can you explain the indirect effect again?
Yeah, sure. So the US has cheaper technology, right? But because the US has cheaper technology, market forces are going to induce the US to undertake more mitigation. Because, if US undertakes X mitigation, that X doesn't apply only to US, it applies to the globe. The rest of the globe is also going to benefit from that X, right? Because emissions is out there in the atmosphere. Gases are all well mixed, as you call it. And so abatement doesn't apply to only one region, it just applies to the globe. And because of that, the US is just going to undertake more mitigation. Although per unit mitigation, the cost for the US is going to be lower. Okay, so basically this is saying that per ton of carbon dioxide abated, the cost for US is going to be cheaper. However, the indirect effect is an effect where you're saying that overall, the US is going to do much more abatement. So the product is just going to make it much more expensive for the US. Make sense now? Okay.
I'm just trying to put this in the context of like a 450 cap as well, right? So if the globe is capped at 550 or 450 or whatever, and the US has more opportunity to invest in technology that reduces emissions, wouldn't industry want to do their business in the US, thus the US?
That's an excellent question. So this exercise here,
I understand.
this exercise here
Yeah.
ignores that effect.
Okay.
It basically says that all that US is investing in technology for is climate mitigation.
Yeah, okay.
And it's not looking at any other
Yeah.
benefits. In fact, when I was preparing this slide, I was trying to think through how to present it in a more, in a much less comical fashion. When I was thinking about, people are talking about this technology race and all that, right? So if you have opportunities to invest, exactly what you said, industries will want to invest more in the US, right? And thereby the US will have more domestic benefits than what is being captured in this exercise. But this exercise doesn't take that into account. In fact, one of my dissertation research actually took that forward, and we accounted for that in that research. If you have perspective for it. Yep.
So what's the net of the two, direct and indirect? What happens?
Sorry?
What's like the net effect?
The net effect
Indirect?
is that if advanced technology is available only in the US, it's going to be more expensive for the US than for the US to just share the technology with the rest of the group. Right? Okay. Yeah. So the important insight from this exercise is that technologies have public goods characteristics. So if one particular country is investing in some technologies, it's not only that country that is going to benefit from that investment. Okay, a lot of the benefits, a large portion of those benefits are going to accrue to parties internationally. And so investments in technology need to be viewed from not a domestic perspective alone, but also include an international perspective. And that is actually calling for a cooperative solution, right? So you're basically saying that technology, when you do technology development and deployment, it's better to look at it from an international perspective. Let's cooperate and arrive at a solution rather than each one investing in the technologies that they prefer or whatnot. In fact, more on the third point is the paper that I was talking about. So we have written a paper where we talked about the value of international cooperation as far as technology deployment is concerned. Okay, the last portion of this presentation will be on the role of institutions. So, in the portions of the presentation so far, we just assume that technology is like they just get deployed, right? But it's not about technologies getting deployed alone, right? what also is important is the space in which technologies will get deployed in the future. And that is pretty unclear. It's ambiguous as to how technologies will evolve given the range of constraints that exist in the sphere. For example, there are institutional capacities which are different in different parts of the world. Do we think that we can have like say 50 nuclear power plants by the end of the century in Africa? Do we can even think of that? Those kinds of things, right? So it's very, very, very hard to even envision those numbers here. There are regulatory constraints. There are policy uncertainties. While we are talking about mitigation policy, there is so much uncertainty whether these policies will actually be implemented and so on, right? People are all talking on the higher level, on the higher level, but we never know. We don't know how these will seep in through the system to the grassroots level. And then public perceptions are so different, right? For example, nuclear has all these political and public eye, right? The technology is always being battered back and forth for that. So, so this particular study that I'm going to present to you was again conducted downstairs as part of my dissertation. The main motivation for the study is that institutional capacities to adopt technologies vary across the globe, right? So you have countries with really poor institutions and countries with very very high quality institutions such as the developed countries, right? And these institutional factors can affect investors' perceptions of risks. So for example, if a firm wants to invest in a wind farm in India versus the US, that firm is going to see a higher cost of debt, which is the interest rate, for the Indian farm as related to the US wind farm, because of a range of institutional risks that exist in India, including things like corruption, bureaucracy, and those things. So in this paper, we explored how does this heterogeneity in investment risks across the globe and across even technologies, right? Different technologies face different risks. Like if you invest in nuclear, you would face more risks compared to coal-fired plant for now, right? I mean, because investing in known technologies is less risky compared to investing in that have all these political risks and so on.
I'm gonna lose the video for a little bit. Keep going, keep going.
Okay. So this paper investigated, the impacts of this heterogeneity in investment risks and how that will impact cost and distribution of climate change mitigation. So in order to do that, what we did, we just focused on one variable, namely the cost of capital, which is represented in the form of fixed charge rates. It's basically the interest rate that a utility would have to pay as mortgage, something like a mortgage, right? So we just varied the cost of capital across technologies and regions in the electricity generation sector, which again, this study is focused on the electricity generation sector because that's one of the key sectors that most studies talk about in climate change mitigation. And we used these institutional quality scores from literature and applied them to represent the variation in the interest rates across technologies and regions in GCAP. In order to represent the variation in investment risks across regions, we also looked at the actual spread in the interest rates. So for example, we looked at lending rates from the World Bank, then risk premium, equity risk premium statistics from Damodaran et al. So Damodaran, and we represented the spread in the interest rates in the model that are consistent with these spreads. And then we explored 4 scenarios. Okay, so you have a uniform investment risk scenario where you have no variation in investment risks anywhere. So all technologies, all regions see the same interest rate, right? And then slowly we just varied the investment risks across two dimensions, one the technology dimension and then across the institutional dimension, right? So you represented variation across technologies and then also varied the interest rates across regions. Okay, so I don't want to take much time since we're probably running out of time. Is it 6 or 7?
Six.
It's
Six.
So do I have like?
You have, yeah, as much as time as you need, yeah.
Yeah, it's just a few more
These,
slides.
these guys are not going anywhere, they're not hungry, they're not hungry, they're not sleepy, so they're good.
Okay, the question is now how hungry and how sleepy am I?
That's another question.
Okay, so let's look at the effects of non-uniform investment risks in the baseline scenario, that is without any climate policy. So the key result here, I can make the slides available later so for you to explore a little bit more, is that with non-uniform investment risks across technologies and regions, there is a reduction in investments in low carbon technologies, right? And the reason for that is that these technologies were applied a higher interest rate compared to fossil fuel technologies, right? And most of these investments tend to come from regions that are really growing rapidly, for example, China, which have lower institutional qualities, right? As a result of these factors, even in the baseline cases, you find a reduction in low carbon technology investments. And an immediate consequence of that is that baseline emissions in the non-uniform investment risk case are higher compared to the uniform investment risk case, right? So when we look at these marginal abatement cost curves, these are again global marginal abatement cost curves for the different investment risk scenarios. What we find is that with non-uniform investment risks, marginal abatement costs tend to be higher, and the reason is again because with non-uniform investment risks, you have the higher cost of capital for low carbon technologies, and again these higher costs of capital are even higher in regions with poor institutions, right? So therefore overall, non-emitting and low carbon technologies tend to have higher cost in these scenarios, in the scenario with technology and investment risks, and that is why you see an increase in the marginal abatement cost. So to achieve 1 unit of abatement, it's going to be more expensive in those scenarios. And so when we explored the impact of including these investment risks in a mitigation scenario, which is basically a 50% reduction in 2050 compared to 2005, and this emissions pathway was obtained by applying a uniform carbon price exponentially rising over time on the uniform investment risk scenario, right? And we just applied the same emissions trajectory for all the investment risk scenarios. And what we found was, again, not surprising from what I just showed you here, is that global costs with non-uniform investment risks tend to be higher, and higher, reasonably higher, 40% higher for the scenarios that we explored. So the question that comes up right now is, who bears those increased costs? So with non-uniform investment risks, with all these institutional factors accounted for, okay, cost of mitigation is going to be higher, but who bears those costs? So when we look at the regional allocation of mitigation burden, what you see is that most of the mitigation or the increase in mitigation is being undertaken by developed countries, right? Like the US or Australia, Canada, and then Australia and so on. And you can see a reduction in mitigation happening in the developing world. Now, so let's look at the reason for that. This is again to do, so this is again to do with the public goods nature of technologies that I was talking about a while ago. So, technologies are cheaper in the non-uniform investment risk case in these regions, in these better institutions regions, and those are the regions that are induced by market forces to undertake more mitigation. as a result of which most of the mitigation burden falls on the regions with the cheaper technologies. And that's just offset by reduced mitigation in the developing world, right? Because they can just free ride on the emissions mitigation that happens in the developing world. So the key insight over here from this study is that, people have been talking about the role of technology, the importance of technology deployment, development, and R&D for low carbon technologies and so on, and their role in climate mitigation. However, what is also going to be important is the environment, or the sphere, the space in which these technologies actually deploy. And major efforts to improve that space need to be a critical element of international negotiations of international climate policy. Otherwise, it's plausible that the global cost of achieving stringent mitigation goals would be reasonably higher compared to what you would assume in the status quo. So I'd like to just wind up with a quick overview of the GCAM team's leadership on the road to Paris. So for just a quick refresher of this issue. So I mentioned early on in the presentation that the UNFCCC is in charge of conducting climate change negotiations, right? So these negotiations happen every year. So around it's a nice political gathering. You can see more videos on YouTube for more spicy descriptions of how these negotiations actually happen. I'm not going there. But all I'm going to say is that the UNFCCC is in charge of doing this. And this year in December, countries are coming together in Paris. They're convening, and they're going to put forth emissions reductions for the near term, that is through 2030. Some countries have committed to emissions reductions through 2025. For example, the US has put forth a commitment of 26 to 28% reductions in economy-wide greenhouse gas emissions by 2025. China has agreed to peak their emissions by 2030, right? So different countries have proposed different commitments, and they're all going to come together in December in Paris. And GCAM team has been playing a very important role in ensuring or in informing some of these negotiations from the side of the US government. And we have written two papers that address two key pre-Paris questions. Right? Before these negotiations actually happen, there are some interesting questions, and we have tried to address two important questions that, among the range of questions that policymakers are interested to look at. The first question is, what do these INDCs imply for long-term challenges of achieving a particular long-term outcome, right? And in this case, we just explored that, let's say that the international community is still focused on achieving a long-term outcome of 2 degrees C. And we also, we didn't necessarily attach a probability, we explored what would be the implications for the long term, assuming that the international community is interested to achieve 2 degrees C with a 50% likelihood. And we ran GCAM scenarios using GCAM to explore the long-term challenges that would be that the globe would likely face. The second question, which is probably the most interesting question, is what would be the probable temperature outcomes of these negotiations? Like, assuming that countries actually achieve the emissions reductions that they're putting forth, or they have been putting forth in the last few months. Assuming that the countries actually achieve them, what would be the probable temperature outcomes? Okay, so these are the two key questions that we have been exploring in the recent past with regards to international climate policy. The first study, I'm not going to go into the details of this. It's forthcoming in environmental research letters, and the key finding of this study is that a successful agreement in Paris will reduce future challenges. A successful agreement in Paris will not necessarily align with the cost-effective trajectory like previous studies have found, but we emphasize that it is very important to look at the counterfactual, which is basically a scenario where the negotiations collapse altogether and countries just decide they're not undertaking any mitigation in the near term. So in that scenario, you can see dramatic emissions mitigations happening in a very short time period of 5 to 10 years, and this is much worse compared to the Paris scenario, in which countries actually achieve their INDCs through 2030 and then decide to catch up with the cost-effective trajectory. So that's the key. That's one key insight. And then if the commitments can be strengthened further, I mean, it's still 2015, and we are talking about commitments through 2030. So if these commitments can be strengthened further, then the implications for the long term will not be as severe. So future challenges can be reduced. Study 2 is unfortunately embargoed. It's upcoming in Science, and it's a work that we have led. Heywan, McChawn, Leon Clark, Jay Edmonds, myself, along with a range of team members in JGCRI and EPA, State Department, and so on. So it's a big team that has worked on looking at what are the probable temperature outcomes of Paris, and I would encourage everyone to look forward to this, look for this paper, which will be out in a few weeks' time. Unfortunately, I cannot show you any results of that here because of the embargo policy.
Not even a small graph? No, I'm kidding.
We can turn the
We've
video
been
camera
advised
off.
not to show results anyway.
I'll turn this off.
Sorry. No, I really wish I could show
No, it's all right, it's all right. We understand.
Yeah, right. So, so probably the most important part of this lecture.
Absolutely.
This is a very simple assignment, considering that many of you are also working on the project proposals and the term project. So you just have to run. The instructions are lengthy, but then it's just a very simple exercise. You've already run this, the 450 cap with a full technology portfolio. The second scenario is to run 450 cap with no CCS. So throughout this lecture, we have seen the benefits of having advanced technology. More primarily, the benefits of just having technology, right? So if you don't have technology, that's going to be you're going to see some interesting results. So the assignment will require you to run the 450 cap with no CCS. So these are the instructions here. The files, the XML files are already available. What I want you to try now, the new thing that I want you to try is to turn on the policy cost calculator. So this is basically a parameter that you will see in the configuration file. So you just have to turn it to 1. So the model will basically run itself 5 times and create a cost curve. I was talking about marginal abatement cost curves. It's going to create that curve and calculate the area under that curve and report that as the mitigation cost or the policy cost for every period. Okay, so you would do that. So the questions that I would like you to explore are as follows. First, what's the global value of CCS? So by value, I mean the policy cost of the scenario for the scenario with CCS minus policy cost without CCS. Probably the other way now. This one is going to be higher. Without CCS will be higher. Does that make sense to you? Yeah, because you don't have one mitigating technology option, so that's the costs are going to be higher. Okay, so just try to look at that. Get a feel for the get a sense for the numbers involved, and then what's the regional value of CCS? Now let's try to look at how the global value compares with the regional value in terms of percentages. So is it the same for China? Is it the same for US, and so on? You can pick one developed and developing country. I would also like you to look at how the availability of CCS impacts technology transitions. So basically, you can look at electricity generation, like how I showed early on in this presentation, use animations, right? And also try to look at availability of CCS and its implications for sectoral and regional distribution of mitigation. So, whereby I would like you to appreciate, how the carbon price-based approach that we typically use in models, need to be viewed with caution, with the caveat in mind that you're assuming equal marginal effort across sectors, and that might not be very. I would like you to comment and think about it, how realistic you think that is. Does that make sense? So any guesses for, just one question, if you can think about, so if I apply equal marginal abatement cost, or if I apply the same carbon price to achieve a global cap, can you guess which country would do the most mitigation?
China.
It's obvious, right? Probably we've already seen that, right? And any reason, guesses for, can you just explain?
We just talked about, we talked about how like the electricity having the dirtiest, being the dirtiest sector, right? So they have the most opportunity to change the quickest, right? If they're,
Right.
But that's electricity, so I don't know. We're talking about industry as well, right? So
Yeah, that's right. So the concept is as follows, right? I mean, if you assume equal marginal cost of abatement across regions or across parties, the dirtiest party will be hit most.
Yeah.
Right? That's the first level understanding. The second level of importance is where those or which sectors will be targeted most. They will be targeted. The supply side sectors will be targeted more than the demand side, right? And so because China is the most emitting region among the GCAM regions.
Well, it's the heaviest in coal.
Even in the
and
world.
It's the highest in supply sector. It's the heaviest in coal.
Exactly,
So
it's heavy in coal,
yeah.
and its baseline involves rapid expansion of fossil fuel-based generation.
Yeah.
Right. So China has in the baseline, no political statements being made here. In the baseline, in GCAM, it has rapid. It has a dirty energy system. So that's going to be worst hit. Right. So I would like you to just look at that and just get a feel for those kinds of concepts. And in the tutorial session, maybe we can just work through a simple example to make you understand the concept of equal marginal cost. Like why is it that dirty sectors are hit more than clean sectors? That's probably something we can do using a simple numerical example. Sound good?
So can we start? How do we actually query for the global value of CCS?
It's just global mitigation cost.
Is that built into the query?
It's built
Query system?
into the query. So it's just one of the
Okay.
queries. You just have to query policy cost.
Okay. Oh yeah, I've seen that. Okay.
Yeah. So you just have to query that and then subtract it from the policy cost of that.
Okay.
And look at percentages so that you can see how that compares with the regional values. So again, the reason I asked you for China, or for which country is going to be emitting or doing much more mitigation, is actually a follow-on question. So can you imagine? It's very easy to understand that China, by virtue of it being the most emitting region, is also going to have more value for CCS, right? So let's see if that's how things play out, or if not, then why not?